One of the important types of the series is called the power series, where the term of the series comes with the powers of the x. So where x is some variable. So here, if I substitute n to be equal to the 0, 1, 2, and so on, we can write down the terms of the series in this form. So when n is equal to the 0, it's going to be c0 multiplied to the x minus a in the power of 0 plus c1 multiplied to the x minus a in the power of 1 plus c2 multiplied to the x minus a in the power of 2 plus and so on. So we are going to denote this term, so x minus a in the power of 0 is equal to the 1 even when we take x to be equal to the a. So the difference between the polynomials and the power series is that the polynomials have the fixed number of the terms and the power series have infinitely many terms. So and also there is a conceptual difference between the series and the power series, right? For example, you can write down the series in this form. N is equal to the 0 to the infinity, x in the power of n, right? So this is an example of the power series. If I substitute n to be equal to the 0, 1, 2, and so on, I can write this in this form. 1 plus x squared plus x cubed plus x4 plus and so on, right? So this is an example of the geometric series at the same time where the general quotient is equal to the x, right? Every time in order to get the next term, I need to multiply the previous one to the x. So the geometric series is convergent, right? When sum of the geometric series is finite, when r, the general quotient, is between -1 and 1, right? So previously, if you're given a series, it is either convergent, either divergent, right? Now it appears it depends on the value of the x as well, right? For some value of the x, in our case, when x is between -1 and 1, the series is convergent, and for all the other values of the x, the series is divergent. So we can write this like this. So the series xn, n goes from 0 to the infinity, is convergent when x is between -1 and 1, and we even know the sum of the series, right? It's going to be the first term, which is 1, divided to the 1 minus general quotient, which is x, right? And the series x in the power of n goes from 0 to the infinity, is divergent for all the values of the x which are not included in this case, right? So when x in the model is more or equal to the 1, basically it is more than 1 or less or equal to the -1. So the values, the set of values where the series or where a series is convergent, the values for the x, right, is convergent, is called an interval of convergence. For example, in our example, the interval of convergence is between -1 and 1. So please note that here the a value means the center of the power series, right? So in our example of x in the power of n, the center of the power series is equal to the 0. So basically, if I would like to write down the interval of the convergence in the interval of the numbers, right? It's going to be the x. So the center of the power series at the 0. And this is convergent when x is between -1 and 1, right? In this interval. So basically, if I'm sitting in the center, the possible values for the x can be between -1 and 1. Or we can say, hey, if you're in the center, you can go to the left or to the right, maximum to 1 unit, so that the series is still convergent. So we can define this distance, so until where you can go inside the interval, to be a radius. So basically, the radius, in our example, the radius of convergence is equal to the 1, right? So the interval of the convergence is between -1 and 1, and the radius of the convergence is simply 1. So let's consider another example and define the interval of convergence and the radius of convergence. So we are given a series in the form n factorials, x in the power of n goes from 0 to the infinity. So in order to test this for the convergence, we're going to use the ratio test. So do you remember, in the ratio test we need to define the nth term of the series. It's going to be n factorials, x in the power of n, and n plus first term. It's going to be n plus 1 factorials multiplied to the x in the power of n plus 1. And we need to find the limit of the ratio of the n plus first term to the x an when n goes to the infinity. So basically, I can write this down as limit n goes to the infinity, n plus 1 factorials multiplied to the x n plus 1 divided to the n factorials x in the power of n. So I can cancel the terms. So basically, we can write down the n plus 1 factorials as n factorials multiplied to the n plus 1. And we can write down the x in the power of n plus 1 as x in the power of n multiplied to the x, right? So divided to the n factorials x in the power of n. And what is left is simply n plus 1 multiplied to the x. So when n goes to the infinity, so this limit diverges, right? It is basically is equal to the infinity, right? So basically our series is divergent, but so do you remember, if you substitute the terms here, the first term here is going to be 1, the second term is going to be 2 factorials x in the power of so 1 factorial multiplied to the x plus 2 factorials multiplied to the x squared plus 3 factorials, which is 6 multiplied to the x cubed, and so on, right? And the center of the series, center A, is equal to the 0. So where x is equal to the 0, the first term of the series is equal to the 1, right? As usual, it is equal to the C0. So basically, this series is divergent, except only one case, when x is equal to the 0. Okay, so the series, the power series in our case, the domain or the interval of convergence, domain of convergence is simply 1 point, x is equal to the 0. So if you find itself in the center 0, right? So the maximum distance which we can travel inside the interval of convergence or domain of the convergence is 0. So that is why the radius of convergence r is equal also to 0. So this example shows us that the power series are always convergent, at least for 1 point. Okay, so now let's consider another example where the interval might be slightly different. Interval of convergence might be different. So, an example. So, the power series is given in the form x minus 3 in the power of n divided to the n goes from 1 to the infinity. So a couple of the first terms we can write in this form. So when n is equal to the 1, it's going to be x minus 3 plus, when n is equal to the t, it's going to be x minus 3 and a square divided to the t, x minus 3 and a cube divided to the 3, and so on. So we are going to test the series for the convergence by using the ratio test. an is going to be x minus 3 in the power of n divided to the n, and an plus 1, it's going to be x minus 3 in the power of n plus 1 divided to the n plus 1, right? So please note that we can write this in the form x minus 3 in the power of n multiplied to the x minus 3 divided to the n plus 1. Okay, so let us write down the ratio test. The ratio test tells me that I need to find the ratio of the an plus 1 to the an in the model and find its limit when n goes to infinity. So this is going to be, when n goes to infinity, x minus 3 in a power of n, x minus 3 divided to the n plus 1, divided to the an, which is x minus 3 in a power of n, divided to the n, and the model. So if we cancel out the terms, it's going to be the module of the x minus 3 multiplied to the limit of n divided to the n plus 1 when n goes to infinity. So when n goes to infinity, this limit is equal to the 1, right? So it goes to the 1. So that is why it can be written as the module of the x minus 3. So the ratio test tells me that whenever this limit exists and this limit is less than 1 in a model, then the series is convergent, right? When the series is convergent in this case. So when x minus 3 is more than 1, then the series is divergent. When x minus 3 is equals to the 1, the test doesn't work, right? The test doesn't work. Basically, the test doesn't know whether the series is convergent or divergent when the limit is equal to the 1. So we need to check these cases separately using the other tests. Okay, so let us write down first of all the interval of convergence. Okay, so before we write the interval of the convergence, we need to check the cases where x and minus 3 in the model is equal to the 1, right, for the convergence. So x minus 3 in the model is equal to the 1 means that x minus 3 is equal to the 1, or x minus 3 is equal to the minus 1. So there are two cases where x is equal to the 4 and x is equal to the 2, right? So let us check them separately. So our series had a form x minus 3 in a power of n divided to the n and goes from 1 to the infinity. So when x is equal to the 4, so our series had a form 4 minus 3 in a power of n divided to the n and goes from 1 to the infinity. So 4 minus 3 is 1, so 1 in any power is going to be 1, right? So the series becomes 1 over n and goes from 1 to the infinity, which is a harmonic series which is divergent, right? So where x is equal to the 1, the series is divergent. So let's consider the second case when x is equal to the 2. If I substitute the 2, it's going to be 2 minus 3 in a power of n divided to the n. N goes from 1 to the infinity. So 2 minus 3 is going to be minus 1, right? Minus 1 in a power of n divided to the n, and goes from 1 to the infinity. This is the alternating version of the harmonic series, so that is why it's convergent. So 2 at the x is equal to the 2, the series is still convergent. So that is why we can write down the domain of convergence. The domain of convergence, the set of values for the x where the series is convergent of convergence, as so x minus 3 in the module is less than 1, and right, and x is equal to the 2. If you open up the brackets here, it's going to be the interval between x is 2 and 4, and we need to add a case when x is equal to the 2. Basically, the domain of the convergence is going to be between 2 and 4, where 2 is included and 4 is not included. And the radius of convergence r is equal to the 1. So let us consider another example where the radius of the convergence is going to be different from 0 and 1. Example. So we're going to consider the Bessel's function of degree 0. So this is defined as the power series n goes from 0 to infinity as minus 1 in the power of n, x in the power of tn, divided to the t in the power of tn, multiplied to the n factorials in the square. So we would like to test the series for the convergence, and we would like to find the values for the x where the series is convergent and divergent. So let us define the nth term of the series. It's going to be minus 1 in the power of n, x tn divided to the t, or let me write this as a 4 in the power of n, right? So n factorials in the square. So we can define at the same time an plus first term, right? An plus 1. So it's going to be minus 1 in the power of n plus 1, x in the power of tn plus 1, right? So that is why it can be written plus 1 in the brackets, divided to 4 in the power of n plus 1 and n plus 1 factorials in the square. Okay, so let me rewrite this in a slightly different form. It's going to be minus 1 in the power of n plus 1 multiplied to the x tn multiplied to the x square, right? Because if you open up the brackets in the powers, it's going to be tn plus t, and you can write down this as a multiplication of the x. So 4n multiplied to the 4 multiplied to the n factorials in the square multiplied to the n plus 1 in the square, right? Because n plus 1 factorials can be multiplied as a multiplication of the n factorials to the n plus 1. So now, using the ratio test, we need to just divide an plus 1 to the an. So let us divide first of all, then we will find the limit. An plus 1 divided to the an in the model. When we divide them in the model, we can just skip the minus 1s in the powers, right? We can write this as x in the power of tn multiplied to the x squared divided to the 4 in the power of n multiplied to the 4 multiplied to the n factorials in the square multiplied to the n plus 1 in the square. So this is divided to the an, right? Or we can multiply this to the reciprocal of the an, where the numerator and the denominator of the an will be just flipped. Okay, so it's going to be 4n multiplied to the n factorials in the square divided to the x in the power of tn, and everything is in the model, right? So we can cancel out the following terms. We can cancel the xtn, 4n, n factorials, and n factorials. So what is left is in the model x squared divided to the 4 n plus 1 in the square, right? So we need to find the limit of an plus 1 divided to the an. When n goes to infinity, it's going to be the limit of x squared divided to the 4 n plus 1 in the square. When n goes to infinity, and no matter what is the x, it's going to be 0. Okay, so basically this is the number which is less than 1, right? So that is why the series, this power series, or basically the Bessel's function, is convergent for all the values of the x, right? So the domain of convergence is between minus infinity to the infinity, right? X can be any value so that the series is convergent, and the radius of convergence r is equal to infinity.